An initial sample of 511 grams of a radioactive substance decays according to the function A of t equals 511 e to the negative 0.043t, where t is given in years. How many grams of the substance will remain after 61 years? Round your answer to one decimal place. Well, let's see. So we have a model, A of t equals 511 e to the negative 0.043t. And what it does is it takes an input value of time, which in this case is in years. So it takes a number of years, and then it will output for us the variable a, and that's an amount. So it's an amount of radioactive material remaining after this number of years has passed. So we want to know how many grams will remain after 61 years. So we can determine the amount of grams remaining if we just let t equal 61. So that means we would evaluate 511 e to the negative 0.043 times 61. And we can do this right in the calculator. It would be 511. If I hit second and divide, I will get an e here. And e, of course, is just the base of the natural logarithm. So it's a number like 2.718. But the calculator knows that to a lot of decimals, so just let it do that. And then we're raising that to the negative 0.043 times 61. And make sure you use a negative sign instead of a minus, because the calculator differentiates the two. If you've got all that, then we have the answer here, which is to one decimal place as requested there, 37.1. And then that's a number of grams. The next part of this question asks, what is the half-life of this substance? Round your answer to one decimal place. So the half-life is an amount of time that it's going to take for the amount of radioactive material to decay to 1/2 of the original amount. So we still have the same model, and actually let me scroll up to get that model. So it's A of t equals 511 e to the negative 0.043t. So what we want to know is how much time is going to have to pass before we get to half of the initial amount. Well, half of the initial amount is 511 divided by 2. Okay, so if we just set our function equal to 511 divided by 2, then that right there is going to give us the amount of time it takes to decay to that amount. So first thing we would need to do is just divide both sides by 511. But what's interesting here is if you work with these fractions, and you can go off to the side and show this if you aren't sure, 511 divided by 2 over 511. Just put this bottom 511 over 1. And so this is 511 over 2 times 1 over 511. So the 511s just cancel. And what you're left with is 1/2. So 1/2 equals e to the negative 0.043t. So what it's saying is basically, if you start with 1 gram of the substance, it's going to take the same amount of time for it to decay to 1/2 of a gram as 511 grams to reduce to whatever half of that amount is. So it's always the same amount of time to reduce the radioactive material by 1/2. Now, to solve this, we have a variable in the exponent of this equation. We need to get the variable out of the exponent. The only way to do that is to change from exponential form into log form. And log form would look like a log base e, because that's the base of my exponential, of 1/2, and that's equal to the exponent itself. So now we're in log form. And of course, a log base e is the same thing as a natural logarithm, so certainly you can just change that over to a natural logarithm, and that way you can use the calculator to solve. Because the only thing we would need to do at this point is just divide both sides by this negative 0.043 to get the variable t by itself. So the amount of time then, if we use the calculator here, would be the natural log of 1/2, or just 0.5 if you like, divided by negative 0.043. And to one decimal place, as was requested, that would be 16.1 as the answer, and then the time was in years. So 16.1 years is the half-life of this radioactive material.